All right, record is rolling. This is Projectile Lab. So you guys have been out. You guys completed this table, did a bunch of launches, grabbed a bunch of data, and we've been back in the classroom for a few minutes now. And you guys are figuring out what's launch speed. Caleb is telling me about 8.5 meters per second, which does sound correct. Now there was a window, right? So you got plus or minus a few meters per second. Earlier got 17. I heard another 8 meters per second earlier. I'm talking about a few periods ago. Don't forget too that there are different mass balls, right? There were light balls and heavy balls, which would make a difference too, right? So not everybody's gonna have the exact same launch speed. You guys have different launchers, right? But what would be the process to figure this out? So let's go to that. I mean, if you want the launch speed, if you did this exact setup, and I'll do some of the other setups later, so some of these, but let's just focus on this one for now, right? Then however fast the launch speed was, well, wouldn't that be this horizontal displacement divided by the time you get from here to here? Right? This d divided by t, but you don't know the t unless you had a stopwatch. But you could calculate the time to fall based on the height of fall. Here's what. You guys remember if you launched one out straight horizontal and you drop one at the same time, to hit the ground at the same time, right? Which is the hint that maybe the vertical motion has something to do with well, it's independent of horizontal motion, right? And however much time it takes to fall has something to do with that height of fall. So here's what we're gonna do. We're going to take this first kinematic formula, since some of you guys figured this out already, and we're going to modify it just for the vertical scenario. So this is the general displacement S. I'm going to use more specifically the vertical displacement H, like a height drop. H goes right there. So I'm looking at vertical analysis, vertical. Remember, this is going to be like a two-part process. The vertical stuff, I'm going to get the time of fall, and then I'll switch over to horizontal here in a few minutes. Horizontal. And then put it all together and figure out the actual launch speed. Okay, so we got H equals, right? So I'm playing off this. Now, V naught, this is really V naught in the Y direction if I'm talking about strictly vertical, right? Remember that's the way we've been analyzing these for the last week, right? We look strictly vertical or strictly horizontal. Right now we're on the strictly vertical part. Okay, so guys, when this ball is leaving this cannon, how fast is it moving up or down right at that moment? 0. Right now, of course, that immediately starts to change as gravity pulls it, but right at the moment, right, of that blast, isn't V naught Y 0? So this piece goes away and just turns into this. And then well, we do have a special kind of acceleration, free fall gravity. I can just put a G right there. So isn't this 1/2 G T squared? Does this look super familiar? Right? We've been using this a lot last couple weeks, right? This is a simplified version. Okay. Hey, here's one place of many times that you saw this. You guys remember the Paul Hewitt story? You walk into a mine shaft, well, like into an okay, there's a mine shaft, you're looking at, I wonder how deep it is. You drop a rock, you count to 5 before you hit the bottom. You see 5 seconds of falling. I wonder how deep it is. Well, 5 times 5 is 25, times half 10 is 5. It's about 125 meters deep. How'd you know that? College, you guys remember that? That was a story told through that formula. Now we're gonna apply it the opposite way. Instead of knowing time and solving for H, you know H, you're solving for time. A couple different numbers for H. Earlier we were using 4, 4.2. I'm here 4.33, 4.36. We take kind of a middle of all that. Let's go with let's call it 4.3, maybe something like that, right? Just to throw a number in there. What do you guys feel like using for G? 9.8 or 10? 10? Sure, let's do it. 10 meters per second squared. Okay. Hey, can you guys solve for the time of fall? Right? Just a few algebra steps, right? We can do that. All right. So let's see, maybe multiply the 2 over 2 times 4.3 meters is equal to 10 meters per second squared times time squared. All right. What's the next algebra step? Divide that 10 down, right? So let's see, t squared would be 2 times the height drop divided by the gravity field, right? And what's the last algebra step to extract t? What do you do to both sides?
Square root.
Square root, that's it. Okay.
So
square root, both sides, balance the equation. Let's see what is the square root of all that fun stuff. 2 by 4.3 on 10. I'm looking at 0.9. Maybe we should call it 0.93. I'll keep another digit though. 0.927 seconds. Right now, that's way too much precision, but that's okay because I'm using this as a middle step. Right, this is just part 1 of 2. Right. Okay, so now I got the fall time. A good thing, a good practice in physics is when you get answers like this, step back for a moment, say, does that make sense? So 0.9 seconds, that's a little bit less than a second, right? Does it seem like it took a little bit less than a second to go from here to here? Yeah, I could believe that. Okay, so let's proceed forward. So in the horizontal direction, now remember, horizontal, guys, is there any horizontal acceleration? No, gravity doesn't pull horizontally, gravity only pulls vertically. So there's no G, there's no A. Air drag. You think we can probably ignore air drag and be pretty close to what happened? Yeah, so let's do that too. Basically, no, and if that's true, it just boils down to if the A is just zero, is it just x equals vt? Except this is sub x, subscript x for in the horizontal direction. I have some version of this. The distance that went, the horizontal displacement, I should say, is equal to v sub x times the time of fall, right? Or if you like, maybe you actually started with this next step, just d over t, right? Is that true? Still algebra rearrangement in terms of variables. Okay. Oh, and what's one average value that you guys got for d? How many meters?
7.7.
7.7. Let's go with it. 7.7 meters. And the time of fall for everybody, regardless of which ball you used or which cannon you used, as long as it was at the same height, should have been 0.927 seconds or so. This is v sub x. Now, v sub x, remember, is the launch speed because you launched it strictly horizontally, right? Unless you didn't, in which case I'm about to show you here in a few minutes what you do. But if you did, my recommendation, then here's what we got. That many meters and that many seconds. Hey, that's extremely close to what Caleb was saying it would be. So I'm looking at 8.3 something meters per second here. He was saying like 8.5. Yep, that is right there in the ballpark. Nice. Okay. Now, again, like I said, different cannons, different balls. I got numbers high as like 17 meters per second earlier for another class. So yeah, it should be kind of in there though. Okay, you guys get that? That worked out for your numbers too?
Mhm.
Okay. All right, now what I want to do with the last few minutes of class here is show you guys the other setups. So let's suppose you had done one where you just blasted straight up in the air. If you did that, I'll do this kind of fast, but we'll just for completion here. You could have gone VF in the y direction squared equals VF initial squared, plus or minus depending on your perspective, 2g h max, right? Now, at the max point, it would have been 0 meters per second. That's what would mark out the maximum spot. You could measure h max, say with the meter stick. You could plug in 10 or 9.8 meters per second squared for g. See how you could do a little algebra and just solve for that? Add this over square root. So v launch would have been square root 2g h max. This is if you did this version, you just did straight up. You said how high does it go? Okay, so that's that version. Right. If you did this version where you had a plane and you just ranked up some angle, let's say like 40 degrees or 50 degrees or whatever angle you pick, okay? V launch would be what? Well, this relates to, do you guys remember from last week, range formula? I derived this with you guys. You guys remember that? Right. Hey, what we applied earlier said if you know the blast speed and gravity field and the angle, you could pop this all in and figure out how far it's going to go. But if instead you measure how far it goes, and you know this and this, could you instead solve for v? Let's do a little algebra. Cross multiply g, divide down sine of 2 theta. V squared equals, what am I getting here? That would go g times x divided by sine of the double angle. Right? And then you could just take square root of both sides. So v launch equals the square root of all that fun stuff. Right? Now that was a little trick here. That would have been a way. Right? And finally, I want to do one last way. Right? And that is, I had one team earlier that went all super funky. They did almost what you did, except instead of launching it horizontally, and ramped it up to a few degrees. Okay. So here's what that would have looked like, and how to have solved this. All right. So I got this cannon. Gonna blast. I'll just call this plane V, and then I'll split the components. This is V sub x, which would have been blast b times cosine of the angle to the horizontal, and b naught y, which would have been blast b times sine of the angle to the horizontal. Then you would have said you had to solve this with a system of equations, which would have been really tricky. Here's h, here's d. I could say the height drop equals v naught yt, which is v sine theta times t, and it'd be in the negative direction if down is positive, plus 1/2 gt squared. You could also say that this distance d equals v times cosine theta, all times the time of fall. Now you could measure all these things, except you would not know what v is, and you also would not know what t is. But you guys see how this would be a system of equations? So that would be your system of equations, and that's what would get you started. There'd probably be a quadratic formula involved in there. All right, you guys have a great rest of your day. Yeah.